We present our work, a parametric analysis of discrete Hamiltonian functional maps. The aim of this paper, as the title suggests, is to perform an in-depth theoretical study of Hamiltonian functional maps, which we introduce here for the first time. This formalism arises naturally when related the eigenfunction of two distinct discrete differential operators, the former being the standard Laplace-Beltrami operator, and the latter being the Hamiltonian operator, its localized version. Here, we show an eigenfunction of the Laplacian on the left and an eigenfunction of the Hamiltonian on the right, which is locally supported. Hamiltonian functional maps allow to build a correspondence between these two eigenbases, and let us pass easily from one to the other. Our goal is to characterize formally this phenomenon, performing a parametric analysis which enables us to understand how the eigenfunction on the left transforms to the one on the right, both from a global and a local point of view. In geometry processing, the Laplace-Beltrami operator is ubiquitous. Its spectral quantities, solution to the eigenvalue equation, capture intrinsic geometric information of manifold surfaces. When dealing with bounded domains, boundary conditions should be imposed on its eigenfunctions. In this work, we impose Dirichlet condition, which constrain the eigenfunctions to vanish on the border of the domain. The Hamiltonian operator can be obtained from the Laplacian by adding a potential term, which is a real-valued function defined on the surface. In this work, we focus on a simple step potential, composed by an orthogonal projection operator P and a real-value parameter tau. This two set the potential to 0 on a certain region, in white, and to a finite value tau on its complement, in red. The value of tau corresponds to the height of the step, and directly identifies with the potential energy. When tau tends to infinity, we recover the well-studied model in physics of the infinite potential barrier. It is well known in quantum mechanics that in the continuous case, Hamiltonian eigenfunction with eigenvalues less than the potential energy vanish on the high potential area, enforcing localization. We can observe this phenomenon by looking at the eigenfunction with the lowest energy. When tau tends to infinity, Hamiltonian eigenfunction will vanish on the boundary of the potential region. This behavior is equivalent to the one enforced by the Dirichlet boundary condition on Laplacian eigenfunction, justifying our previous choice. The same equivalence holds with isometrically deformed surfaces, due to invariance properties of the Laplacian eigenfunctions. Our aim is to study the dynamic process depending on tau, which evolves the Laplacian basis to the Hamiltonians. To achieve this, we employ the functional map formalism. A functional map is a linear operator between the functional spaces defined on manifolds. It allows to tackle correspondence problems by mapping functions between surfaces, instead of considering points. In our case, the Hamiltonian functional map gives the correspondence between the full Laplacian eigenbasis on the top row and the Hamiltonian basis on the bottom row, on the same domain. But what do these Hamiltonian functional maps look like? In this picture, we show the full discrete representation of Hamiltonian functional maps evolving with the parameter tau. We increase the potential energy from 0 to infinity and observe how the maps are changing. At the start, when tau equals 0, we have an identity, because the Hamiltonian is equal to the Laplacian. When we start to increment tau smoothly, the diagonal separates into two components, converging to two slanted diagonals. The goal of the paper is to characterize mathematically the structural evolution of these maps, which we observed experimentally. The visualization of this phenomenon, although interesting, does not provide much information on the underlying process. We could instead gather more knowledge by analyzing the parametric evolution of the eigenvalues. In this slide, we show how eigenvalues evolve while increasing tau. On the x-axis, we have the values of tau, and each curve shows the indexed eigenvalue ordered increasingly. Here we show the first 20. The evolution of the eigenvalue curves displays some interesting irregularities. They increase monotonically, and often seem to interact by repelling one another. We notice that the eigenvalue curves stabilize after tau has reached a certain value. On the right, we show two eigenfunctions with different indices, the 10th and the 20th. We notice that the lower index eigenfunction on the left converges faster, in contrast to the higher index eigenfunction on the right. This is related to the fact that the eigenvalues curves stabilize at different values of tau. It is clear that before convergence the eigenfunction transforms in a complex way. We will discuss in detail the nature of this transformation in our analysis.
Our theoretical analysis investigates the dynamics of the eigenvalue curves and that of the associated eigenfunctions in the discrete setting. We have divided the spectral analysis in two main steps. The first is an asymptotic analysis that will tell us how the spectral quantities behave when tau tends to infinity. The second analysis is local in nature and explains the interactions between eigenfunctions when eigenvalue curves come close to each other. Local interactions then will be quantified according to a metric called veering index. Finally, we combine asymptotic and local information to give a mathematical description of the Hamiltonian maps. In order to perform our analysis, we used perturbation theory, a branch of quantum mechanics that studies perturbation of differential operators. The tools that we require are specified by the equations which describe the rate of change of spectral quantities with respect to the parameter tau. We need first and second order eigenvalue derivatives and the first derivative of the eigenfunctions. We notice that each equation contains the inner product between pairs of eigenfunctions weighted by the mass matrix A and the projection matrix P of the Hamiltonian. This quantity is called model coupling and influences the intensity of a spectral interaction. With the equation presented in the last slide, we have proven the first theorem of our paper, which characterizes the behavior of eigenvalues and eigenfunctions when tau tends to infinity. We indicate with k0 the r vertices on the zero potential region, and with k1 the n-r vertices on the high potential region. The thesis can be divided into two parts. The former is related to the smallest r eigenvalues. We have proven that their limit is finite and bounded by the lowest and greatest initial Laplacian eigenvalues, mu1 and mu_n. The limit of the derivatives of these eigenvalues is 0, and the components of the high potential of the lowest eigenfunction is 0. More interestingly, the other n-r eigenvalues will tend to infinity, their derivative tends to 1, and the associated eigenfunctions are equal to 0 on the low potential support. Let's look at what this result means in practice. First, let's concentrate on the eigenvalues behavior, visualizing a simplified real example. We consider a tetrahedron and put the high potential on two vertices. We see that two eigenvalues converge to finite values with derivative equal to 0, while the other two diverge, with derivative equal to 1. The most important aspect of the theorem, however, relates to eigenfunctions. Here we consider a Laplacian eigenfunction of a given index and observe that when tau is large enough, it will be decomposed into components. One on the low potential region, which corresponds to the body of the elephant, while the other on the high potential region, on the head. This shows that the continuous domain quantum mechanical results are not valid in the discrete setting anymore. There exist eigenvalues with value less than tau, whose eigenfunctions do not localize on the region of low potential, but instead on the complementary high potential region. Now let us look at local interactions between spectral quantities. Principally, we want to study the behavior of two eigenvalues curves when they get close enough. To do this, we use the second derivative equation presented previously. We see that the denominator in each sum are high for indices different from j and I. Thus, the contribution in the sum given by eigenvalues different from I and j are negligible. We can perform the following approximation considering only the contributions of lambda I and lambda j. We notice that these expressions have the same absolute value and the inverse side. If the curves come very close, the denominator component gets smaller and the second derivatives increment, meaning that they bend and repel each other. This interaction is called a veering interaction. But two curves may cross only if the model coupling in the numerator is zero, because in that case the second derivative would be null. Now let us discuss how the eigenfunctions associated to two veering eigenvalues interact. Using the perturbative equations, it is not difficult to see that when eigenvalues curve veer, the associated eigenvectors rotate on a plane. You can observe this phenomenon in the left figure. When eigenvalues begin to veer, the eigenfunctions in blue change with the derivatives in red. At the end of the veering interaction, as we can see, the transformed eigenfunctions have swapped the eigenspaces. In an ideal veering case, when the second eigenvalue derivative becomes an equality, a perfect exchange takes place. In general, however, only approximate rotations occur. The interacting eigenvalues will be associated with linear combinations of the initial eigenfunctions. To spot where eigenvalue curves veer, we can use a specific metric denoted as veering index, introduced in the structural mechanics literature. This metric takes into account two factors: the cross-sensitivity quotient that measures the intensity of the model coupling, and the model dependency factor that measures the degree of approximation made on the second derivative. We show an example of the veering index corresponding to two eigenvalues interacting on the shape of a band. The veering index peaks nearly at 1, its maximum, indicating an approximate exchange of eigenfunctions. This metric can be exploited to track automatically eigenfunctions along perturbations of tau, following the path with stronger interactions. Exploiting the asymptotic and local analysis performed, we are now able to present our main theoretical result, namely the parametric characterization of the Hamiltonian function map structure. Recalling that eigenvalue curves have only horizontal and oblique asymptotes, we make the fundamental assumption that all veering interactions are perfect, that is, the veering index peaks always at 1. This case is ideal, but simplifies the analysis enough to make it tractable. With this assumption in mind, let us first look at the following two examples. On top, we see the interaction of four eigenvalue curves. The asymptotes are drawn in black, while the underlying eigenvalue curves are illustrated by the dashed blue lines. Let us focus on the first asymptote that we highlight in red. The starting eigenfunction is phi1 and is exchanged twice on the eigenvalue curves, snapping to the red asymptote. Underneath, we observe the corresponding functional map that changes accordingly. In a certain sense, an eigenfunction flows along the asymptote. We can now illustrate the general case. We start by depicting the map as a matrix C, and consider the first Laplacian eigenfunctions that have horizontal asymptotes. Since there are no crossings, they map in the self, and the corresponding entries in the map will stay diagonal. Now we consider the last Laplacian eigenfunctions having oblique asymptotes. As for the former case, no intersection occurs between them, so the corresponding entries in the map will be diagonal as well. At this point, we take into account the first eigenfunction with an oblique asymptote, depicted in blue in the central section. This eigenfunction must map in the lowest index Hamiltonian eigenfunction on the high potential area psi r plus 1. Its entry therefore will be distributed on the right half of the map. Symmetrically, we look at the last eigenfunction with a horizontal asymptote depicted in red in the central section. This eigenfunction maps in the highest indexed Hamiltonian eigenfunction on the low potential area psi r. Its entry will be distributed on the left half of the map. Based on the arrangement of oblique asymptotes, some Laplacian eigenfunctions will map on higher indexed Hamiltonian values on the high potential area, C2 component, and their entries will slide to the right. Conversely, given the arrangement of horizontal asymptotes, Laplacian eigenfunctions will map on lower indexed Hamiltonian values on the low potential area, the C1 component, with their entries sliding to the left. Each row of C1 and C2 contains a column match, but not both, since an initial diagonal entry slides on the left or on the right depending on the asymptote. We recall that the structure that we have presented is an ideal construction. However, we can generalize to the real case by the following decomposition of the Hamiltonian. The LD matrix is the diagonal of the Laplacian, while the LO the off-diagonal component. Since LD plus tau p is diagonal, the eigenvalue curves coincide with the asymptotes. It follows that this matrix has an ideal spectral dynamics as described in precedence. Applying Wells inequality, we can bound the real eigenvalues to the ideal ones using the lowest and greatest eigenvalues of LO. This perturbation gives rise to non-ideal veering interactions, which cause off-diagonal dispersion in the function map as well as in the corresponding figure.
To characterize the practical usefulness of Hamiltonian functional maps, we present an application to solve the partial shape matching problem. Given a source shape M and a target shape N, which we assume to be an early isometric deformation of a subset of M, our aim is to find a correspondence between these two shapes. We do this by exploiting the Hamiltonian functional map formalism in a fully spectral and automatic pipeline. We split the correspondence problem into two subproblems, often seen interchangeable in the past literature, but which we find complementary. The former is to find an Hamiltonian functional map C between the Hamiltonian eigenbasis on M and the Laplacian eigenbasis on N, while the latter is a region localization problem, where we seek the region V on M, which corresponds to an isometric deformation of N. Our approach is iterative. First, we estimate a map C between the two eigenbases, exploiting a set of arbitrary descriptors in the spectral domain, in addition with a set of regularizers on C to better attain a local minimum. Then, we guess the region V corresponding to N localized on M by transferring an indicator function in the spectral domain, exploiting the current estimate of the map. We can optimize for V starting with this guess, by aligning the spectra of the Hamiltonian and the Laplacian, using a method previously explored in the literature. As a last step, we recompute the Hamiltonian eigenbases according to the new potential region, obtained as the complement of the current estimate for the region V on M. We can repeat these steps until we converge to a satisfactory solution. Our pipeline, leveraging on the relationship between the Laplacian and the Hamiltonian eigenbases, places itself at the state-of-the-art from a quantitative perspective. Our approach offers qualitatively better results than previous one, encouraging solutions which correspond to contiguous regions, and therefore attaining a better performance in the case of symmetries, which are notoriously more difficult to handle. In this work, we perform a parametric analysis of the Hamiltonian functional map formalism. In future developments, other than finding more applications which could benefit from the theory developed, our analysis could be in principle extended to handle more complex eigensystems, such as Hamiltonians with potential depending on more than one parameter. We show two preliminary examples of this. The former is a step potential Hamiltonian, where we study the variation of the area of the potential region. The latter takes a more general perspective, considering geometric deformation flows, where one must also take into account the change of domain across time. Here we show experimental evidence of how spectral quantities change under the action of formalized mean curvature flow.